Okay, welcome. This is Vectors Part 5, Relative Velocity. We're going to be looking at how, when there's more than one velocity involved, how they are relative to each other. So first we're talking about frames of reference. A frame of reference is the position from where the observer, quote, sees the motion. For example, if you are on an airplane flying at 600 miles per hour and you see somebody walking up the aisle, they could be walking at 3 miles per hour. But if someone from the ground could see that person, they'd be going 603 miles per hour because the velocities in the same direction would add. That's true. If someone else is passing in another plane going 500 miles an hour in the opposite direction, they would see that person going 1100. They would see you going 1100 miles per hour because they're in the opposite direction. You, all the time, you pass people on the freeway with a relative velocity of 120 miles per hour. That is, of course, if you go in an opposite direction. So frames of reference are important. Sometimes they're implied, and sometimes they have to be specifically mentioned in the problem or the situation. So two-dimensional relative velocity is when the velocities are independent of each other. That means they both act upon an object as if the other object wasn't there. For example, if this is a boat heading straight south across a river that's running east, then it ends up there are the two velocities, the boat's velocity and the river velocity, they add together, and we normally, of course, add vectors head to tail, and so the resultant would be that the boat actually goes downstream and across at the same time. The east velocity, that would be the river, takes it down the river, and the south velocity, which is the motor of the boat, it pushes it across the river, and the resultant velocity is it results in a southeasterly direction. So if you were standing on the shore, you would see the boat going along the purple vector. If you were sitting on the boat, then you would note the red vector. It was as though you're going straight across. And if you were floating down the river, of course, you would note the blue vector. No, so this is where two velocities are acting at the same time on an object, and the result is the sum of the two, as we've added before. So here's an example. Let's take that motorboat. A motorboat can go 11 meters per second in still water. If that river that we saw in the picture is flowing at 3.5 meters per second, what's the velocity relative to the shore if it's heading downstream? Well, obviously, because if it's heading downstream and the river's going downstream, then their velocities would add together in the same direction, and the resultant would be the sum of the two. So they'd be going 14.5 meters per second. Pretty logical. What if that boat is heading straight upstream? So now we have the water going towards the east, and we have the boat heading upstream, or to the west in this case. So the resultant, recall, goes from the open tail to the open head. So it ended up now, we were going to subtract the two magnitudes, and so it's only going 7.5 meters per second. Those two are pretty simple, straightforward, but both of those velocities are acting on the boat at the same time. Now, what if this motorboat that's going 11 meters per second could go 11 meters per second in still water, is in that there, and it heads straight across. So now we have the boat heading straight across. That represents the 11 meters per second. We have the water going to the right or downstream at 3.5 meters per second. And then, of course, the resultant, as we showed earlier, is going to be the hypotenuse of that right triangle. And so we're going to calculate that using Pythagorean theorem. And so we're looking for what will be the resultant velocity. So we take the 11 squared plus 3.5 squared, sum that, and square root it, and so we get 11.5 meters per second. That's what somebody on the shore would measure that boat traveling. Now, we also, because we're talking about velocity, we have to also calculate what angle it's going. So we put the theta inside the triangle, and then we take the opposite side, which is 3.5, over the adjacent side, which is 11, and we can calculate that it's going 17.7 degrees downstream. Remember, this is relative to the shoreline or somebody standing on the shoreline. Now, what if the boat needs to get straighter? It needs to go straight across. So let's say there's a ferry dock straight across, so it has to do that. Think about what direction the boat would have to go. Okay, so if you were thinking that it has to head upstream, you were right. It has to, because the river is pushing it back downstream, and now the resultant, look at this, is actually the adjacent side to the angle, and the 11 meters per second is the hypotenuse. Now, what do you guess that resultant is? Remember, this is 11 and that's 3.5. Well, let's calculate it. Now we're going to take the 11, which is the hypotenuse, and subtract the 3.5 in the Pythagorean theorem to calculate, and of course it's going to be smaller than the hypotenuse, so it's only going to be 10.4 meters per second. What about the angle? Logically, you're probably thinking that it's going to be the 17.7, but actually mathematically it comes out to, we're now going to use the sine because I don't like using this calculated value if I don't need to. So it actually comes out to 18.5 degrees upstream, a little bit more than when it was heading straight across. So you have to be careful with the wording on whether it needs to go straight across or if it heads straight across. Those are going to be the tricky things in these problems you come across. Okay, here's an example. Let's say we have this airplane that heads due south at 175 kilometers per hour, and the wind is blowing due east at 85 kilometers per hour. Two questions we're going to ask is, what's the plane's ground speed, and what heading is it actually going? Okay, so the ground speed is the relative velocity from a stationary position on the ground, or what would you see or measure from the ground by seeing the plane. So we have this velocity of the plane heading straight down, and we have the wind. So we want to put the wind velocity on the end to add the two vectors. And then the resultant, of course, is going to be the hypotenuse. So very simply, that calculation is Pythagorean theorem, 175 squared plus 85 squared, square root that. And that is 195 kilometers per hour. So that velocity, faster than the straight velocity, but not the total sum of the two. The next question, what heading is it actually going? So we have to find the angle and put it right inside the right triangle, and then we have the opposite side and the adjacent side, so we're going to calculate that with the tangent, 85 over 175. Calculate that in degrees, and it's going to be 26 degrees, and we're east of south. So the measured from the ground, it would be traveling along that vector, still pointing south, but sort of moving. It's going to appear to be moving sideways. By the way, it's a very strong wind, 85 kilometers per hour, for that airplane. Okay, got that? Let's say that this airplane still can only go 175 is still there, and 85 the wind is going. What direction must the plane go if it needs to go due south? So we have this situation again where it needs to go straight south. And so we put the wind and its velocity out this way. So it's just like that boat. So now we have 175 kilometers per hour as the hypotenuse of the right triangle. And so to get the angle, we have to label what angle we're getting. And now, instead of the tangent, we have the opposite side and we have the hypotenuse. So it's going to be, it's going to be the sine. So we take the inverse sine of 85 over 175, calculate that in degrees, and we get 29 degrees. And this now is going to be west of south, because this is our south reference, and the angle is 29 degrees. Okay, the next question is, what is its ground speed now? Remember, that's what is observed by somebody on the ground, and that's going to be the purple one there, the one where it's going due south. So now we have two sides of a right triangle, so we're going to find the third, but one of them is the hypotenuse. So this time we're going to take the 175 squared minus the 85 so that we can calculate the adjacent side to the angle. And that comes out to 153 kilometers per hour. So this plane needs to go south, so it has to head 29 degrees, sort of upwind, if you will, sort of like the upstream, like the boat. And then it's going to be traveling, even though it's trying to go 175 kilometers per hour, it's only going 153 kilometers per hour. So remember that. So if you ever have to calculate the time to go a distance, you want to do the distance that's in the same direction that the velocity's in. Okay, I've added a relative velocity worksheet that's got about 4 problems on it, so I want you to do that. If you have any issues or need to ask me questions, you know how to get a hold of me. Thank you for listening to Todd Academy. Okay?